Yeah, 75% are working from home. I thank you very much for joining this webinar.
Well, it is a pleasure for me. You know that we have a very long-lasting tradition of support to Indonesia, above all through technical cooperation, but also with other mechanisms. Yeah. So I would say is perfectly in line with our long-lasting cooperation with you, and in particular with Batam, but also with other bodies in Indonesia. Bapetan, etc.
Yeah. That's good. Okay. Yeah.
Good.
Maybe we'll start in 2 or 3 minutes. So please wait a moment.
Yeah, we understand very well the technical difficulties. Is not. We are all learning slowly how to manage these virtual events, and I'm also pretty primitive. And fortunately, I have my colleagues, and in particular, Hadid and Chirayo, that they are, and also Rami, I think, that is also connected. They are really supporting me because I'm a little bit primitive with respect to the nerds.
No, all of us like that. You know. Yesterday I got the dry run for the impro site event. We found some technical problem because not everyone could access the WebEx system apparently.
Yeah, there is also this story that we are not using the same IT platform.
Right.
As the other for security reason, we cannot use the Zoom. We cannot download the Zoom. We can use it, but also through as a browser. You know.
Yeah, so I understand. Yeah. So it's different policy. I understand. Yeah. Okay.
So it's a lack of standardization, like for nuclear power plant.
So hopefully SMR could be standardized.
Let's see, because there is a lot of discussion on this standardization, but I still have to see. But anyway, we are off record in this moment.
Okay. So we will be hearing for you and your other speakers then. Okay, it's interesting because next Monday we start the GC, and I have to follow it from office or even from home because with the time difference it's not quite easy.
I understand. Yeah, it's particularly tricky when we have multilateral meetings.
That's right.
And then, of course, there are different time zone, and coordinate all of that is not trivial. Yeah.
It is interesting, you know.
Yeah, it's interesting. However, I'm a little bit old-fashioned, and I hope that we will come back to our normal way to communicate. Of course, all these virtual platforms are very convenient, and of course they are very useful in this situation. But I really hope that very soon we'll come back to our normal way to deliver. I like human direct contact.
Yeah. Okay, let me check to my colleagues whether they are ready to start or not. Sorry, I will mute my speaker then.
Before we begin the webinar, I would like to request your attention to the following protocol. The webinar is to be conducted in English, and all mics will be muted. For the discussion session, it will be held at the end of all presentations. You may use chats to ask questions, either via either in English or Indonesian language. The materials of the presentation will be given in the attached link, And you can also register your attendance to receive the certificate from the organizer. The webinar will be broadcast live via YouTube. We have two links here by Batan and by the Ministry of Research and Technology. To begin with, we have the Minister of Research and Technology of the Republic of Indonesia, Head of the National Agency for Research and Innovation, here with us. Distinguished Minister, Professor Bambang Brojonegoro, welcome to the webinar. We have Chairman of the National Nuclear Energy Agency of Indonesia, Batan, Professor Anhar Risa Antariksawan. We also have representative from the International Atomic Energy Agency. We have Director of Division of Nuclear Power here with us, and also Mr. Stefano Monti. We have speakers from the SMR technology developers from NuScale Power, Rosatom Overseas, KRI Korea, EDF France, and CNNC China. Representatives and participants from the Ministries, Nuclear Agency, Regulatory Body, Industries, Universities, and other organizations, and also observers. Welcome to the International Webinar on Technology Readiness and Safety of Small Modular Reactors. This webinar is organized by the National Nuclear Energy Agency of Indonesia, Batan, as a series of activities to commemorate the 25th anniversary of the National Technology Awakening Day, or Harteknas of Indonesia. To begin with, I would like to welcome Chairman of the National Nuclear Energy Agency of Indonesia, Professor Anhar Risa Antariksawan, to give the welcoming remarks. Your floor, Chairman.
Thank you. His Excellency, Minister of Research and Technology, Chairman of National Agency for Research and Innovation of Indonesia, distinguished representative from the International Atomic Energy Agency, IAEA, Mr. Do-hee Han and Mr. Stefano Monti from Division of Nuclear Power, distinguished speakers, Ms. Cheryl Collins, Director of Sales of NuScale Power, United States of America, Mr. Anton Moskvin, Vice President of Marketing and Business Development of Rosatom Overseas, Russia, Mr. Han Ok-kang, Director of Smart Project of KRI, Republic of Korea, Mr. Benoit Lepu, Director of Development of EDF, France, and Mr. Bin Chen, Assistant Manager of Synergy, China. Distinguished expert panels, participants, ladies and gentlemen, good afternoon and good morning. First of all, I would like to welcome you all in this international webinar on nuclear energy entitled Technology Readiness and Safety of Small Modular Reactors. This international webinar is organized by National Nuclear Energy Agency of Batan with full support from Ministry of Research and Technology, National Agency for Research and Innovation, to celebrate 25th Technology Awakening Day, which takes the theme Innovation as a Solution. Speaking of innovation, small modular reactors, or SMRs, is an innovation in nuclear energy technology, small in electricity capacity generation, but modular in fabrication and construction. The innovative SMR design offers the advantages such as better affordability, higher level of safety and security, shorter construction time, and interestingly, could be integrated with renewable energy to create less carbon emission energy system. These advantages will hopefully ameliorate the public acceptance of nuclear energy. Distinguished ladies and gentlemen, Indonesia can benefit from SMR deployment and its development. Currently, large nuclear power plants are suitable mostly for Java Island, where most of the Indonesian population reside and the electricity demand is high. Meanwhile, in regions outside of Java, such as Kalimantan, due to limited infrastructure and significantly lower electricity demand. In such case, the SMR, which has the capacity up to about 300 megawatt electric, will be suitable for those regions. It would also open the opportunity for Indonesian experts to involve in the development of the SMR, as there are still room of design improvement and SMR design in general. Although SMR may be promising, questions still exist on its readiness, either from the technological point of view, economic or industrial capability. Concerns also pointed out that SMR itself is a new technology that is yet to be proven in commercial scale. To address the question, this webinar is intended for the participants to understand the technological readiness of SMR, including the safety and economic aspects. This webinar will provide valuable insight for Indonesia to be able to exploit the benefit of the SMR designs, especially which are based on water-cooled technology, through the presentation by and discussion with the experts coming from the IAEA and SMR's technology developers. This webinar would also be useful for Batam and other national nuclear stakeholders who actually are assigned to conduct the feasibility study of nuclear power plant construction in potential sites in Indonesia and who are doing R&D in reactor technology. Before closing this welcome remark, I would like to extend my sincere gratitude and thanks to Excellency Minister of Research and Technology, Chairman of National Agency for Research and Innovation, for giving keynote speech and open this international webinar. Thanks also goes to Mr. Stefano Monti and the IAEA for the continued support to Batam and Indonesia, and also to all speakers for their willingness to share the knowledge and information on the SMR design and to expert panel as well. Finally, I do hope that this international webinar could be run smoothly and beneficial for all of us. I thank you.
Thank you, Chairman of Batam, Professor Anhar Risa Antariksawan. Ladies and gentlemen, we will have now the opening and keynote speech by the Minister of Research and Technology of the Republic of Indonesia, and he's also the head of the National Agency for Research and Innovation, His Excellency Professor Bambang Permadi Sumantri Brojonegoro. We would like to invite the Minister now to open the webinar and deliver the keynote speech. Give you the floor, Minister.
Thank you, Ibu Johanna. Assalamualaikum warahmatullahi wabarakatuh. Very good afternoon, everybody, and maybe very good morning and very good evening for speakers or participants from other parts of the world. Chairman of National Nuclear Agency of Indonesia, Batam, Prof. Anhar Risa, Honorable respected representative of International Atomic Energy Agency, Mr. Stefano Monti, and also other experts from IAEA, and also respected representative of NuScale, USA, Rosatom, Russia, EDF, France, Kairi, South Africa, and Chinergy, China. Distinguished participants, ladies and gentlemen, it's my pleasure that we have this very informative meeting directly from the expert on this important topic. As it sounds, in which nuclear sounds like nuclear, it is essential to have the perspective that nuclear energy is really new and clear. The fact that nuclear energy is new is undeniable, because among around 450 nuclear power plants operating in the world today, none of them contribute to electrifying our national development, the country, which is hunger for electricity. If finally we have our first nuclear power plant, then it is new for us as a nation. Hopefully, we can strive our best to have this new power to support our national development. The national development has reached some milestones. The exploration of nuclear energy source of uranium has been demonstrated at Kalimantan Island since 1980. The government is maintaining those energy sources and human resources on uranium mining by establishing the Natural Laboratorium for Exploration. Thorium has been explored as well in several islands in Indonesia. The process from exploration to fabrication has been conducted at Batan for uranium and thorium sources. Moreover, the specific capacity building for human resources on research and engineering has established conceptual design of small nuclear power plant supported by IAEA and collaborated with some national state and private engineering companies. The design improves Indonesia's human resource hard skill through high computation of nuclear reactor and thermal hydraulic experiments, which stimulates the accidents happening in our laboratories. Indonesia, in a similar scheme of human capacity building, also considers the operation and maintenance of 3 research reactors for decades. Therefore, Indonesia has also established a national regulation and regulator, namely Indonesia Nuclear Energy Surveillance Agency, or BAPETEN, for implementation and license of nuclear power plant at land-based condition. The national industry on the application of nuclear technology provides some radioisotopes produced by our nuclear facilities, including research reactors. Those productions are fulfilling the national market demand that's increasing year by year. The medical purpose gives the hospital capability to help people, especially for those undergoing the cancer treatments. In other aspects, mineral mining also utilizes some techniques for logging and process sensing of chemical plants by using radioisotopes such as cobalt-60. Regarding the clear factor, first, many have claimed that nuclear energy is a solution for clear energy needs in our national development. Nuclear has also fulfilled the sustainability aspect and our national commitment in suppressing global warming. So it is essential that we all understand how clear nuclear power plants are. According to IAEA's Integrated Nuclear Infrastructure Review, or INIR mission in 2009, Indonesia has established 15 infrastructures for nuclear power plant implementation. However, only 3 infrastructure left to be established by Indonesia. One of those most important strategies in pursuing infrastructure is national position. Besides, nuclear technology is clear in terms of environmental effect. Also, it is safe from technological standpoints. Yes, there are risks related to nuclear power technology, as also in other technology. Being able to identify all the risks, then plan and prepare to mitigate those risks is the best way to move forward with this technology. I realize some people might still have a negative stigma on nuclear power, but hopefully after this webinar, the number will be decreasing. The communication based on real and scientific data is vital in this manner, and I really hope that kind of communication as this event can be held involving related stakeholders. To pursue those national positions, the consideration involves some assessments that include multi-criteria of the nuclear power plant's importance. National and international cooperation, regulation development, and continuity of the program between national stakeholders. All assessments are mostly done by following the presidential decree, which states that nuclear power plant must consider multi-criteria, assess the technical safety, and last option energy that could be interpreted since the demand could not be fulfilled by all other new and renewable energy resources. Furthermore, the assessment will be a decision basis for national political support with the aims of go nuclear option. In parallel, the national stakeholder prepares a roadmap for nuclear power plant implementation, which is led by Ministry of Energy and Natural Resources, Technology and Site Selection, which is coordinated by National Nuclear Energy Agency of Indonesia, or Batan, as well as licensing, which is conducted by Indonesia's nuclear regulatory body, Bapeten. In our national context, our speakers are beneficial for us to have a clear understanding on how our nation prepares to have our first nuclear power plant. I really appreciate how Batan, in collaboration with other agencies, prepares our national capacity from site selection, nuclear fuel, nuclear reactor operation and safety, also nuclear waste technology, and all the required infrastructure in the frame of the National Nuclear Energy Program. Safe operations of 3 nuclear research reactors in Serpong, Bandung, and Yogyakarta are huge capital in our capacity related to nuclear reactors. The utilization of these 3 research reactors for nuclear technology research and development, radioisotope production, neutron activation analysis for material, as well as for education activities, shows us the capacity of Indonesia to operate these reactors safely. Again, also my gratitude goes to IAEA for their intensive support for our national preparation for our first nuclear power plant. Last but not least, to have clear concrete pathways toward realizing nuclear power plant in our land, clear information about the available technology to be utilized is crucial. Information from the IAEA and the vendors presented here is crucial. I really hope it will contribute to compiling our further detailed steps to create the nuclear power plant. And hopefully, we can build the power plant prototype in West Kalimantan as part of our national research priority. Having a nuclear power plant is not a simple thing. It needs a strong collaboration of many stakeholders. I hope this event may further stimulate symbiotic collaboration among many institutions from governmental agencies and international agencies such as IAEA, also the national, international, private industries. Here, I again state our commitment from the Ministry of Research and Technology, National Agency of Research and Innovation to support this important yet challenging initiative. So by saying Bismillahirrahmanirrahim, the international webinar on technology readiness and safety of small modular reactors officially open. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much, His Excellency Professor Bambang Brojonegoro. It's quite important that you support the nuclear program in Indonesia, and also that it's crucial for the presenters today to deliver their presentation and deliver the data, the information for us to be able to compile all this information to move further with this program. So before we continue the presentation from the IAEA and technology holders, let me inform you on the importance of key aspects that we want to hear from the speakers. We need to address the billion-dollar questions from our government, from the ministry, which SMR technology is available for the near-term deployment. There's also a question on the economics, cost and electricity price, and also the financing, what sort of financial scheme that can be offered. This is also a very important question. And what will be the deployment scheme and the roles of our national stakeholders and industries. And most importantly, how safe is small modular reactor technology compared to the existing operating nuclear reactors, and what has been done by the technology holders on their design based on the lessons learned from Fukushima. Ladies and gentlemen, the agenda for today, we will have presentations from the IAEA, and then it will be followed by presentations from 5 speakers from SMR technology developers, and then we will have discussion, question and answering. So our first speaker today is Mr. Stefano Monti from the International Atomic Energy Agency. Mr. Monti is currently the section head of the nuclear power technology development at the IAEA. And we are also pleased today that the director of the Division of Nuclear Power in the IAEA, Mr. Do Hee-han, is also here with us. So, without further ado, I would like to invite Mr. Monty to deliver his presentation. You floor, Mr. Monty.
Thank you very much. Thank you very much, Ms. Yohari, Minister of Research and President of Bataan. It is really a great pleasure to be here with you today. As I said before, we have a very long-lasting, let's say, tradition of support to Indonesia. We really tried to help this country to adopt nuclear power in a safe, safeguarded and security way. And I also would like in this frame to bring you the best wishes from our Director, Do Hee-han, who should be connected with us, and also from our DDG, Mr. Mikhail Chudakov. So I have a very long presentation, so I think that is better that I share with you immediately my slides, which were really prepared with grand details by our common friend Adit Subki, was really key in supporting me for this endeavor. So as said, we have prepared as requested, we have prepared the presentation on SMR focusing on technology development for near-term deployment, because the understanding is that as said by Ms. Yohari, you wanted to understand what are the reactor technology which can be available in the SMR domain in the near future, so that you can of course prepare your nuclear program in coherence with this technology development and the deployment of SMR. So let me go quickly through the outline of my presentation. We think that in order to put SMR in perspective, first of all, we should understand what is the situation, very briefly, the situation of nuclear power capacity in the world, in the different regions of the world. Then why SMR? So I explain the rationale for the development and early deployment, hopefully, of the SMR. We can also have a look at what presumably will happen in the next 10 years, in this decade, in terms of deployment. Again, trying to address the need for the near-term deployment. Of course, as usual for any technologies, not only about nuclear, for any advanced technologies, there are advantages, but there are also, of course, issues and challenges, above all when we talk about the development and the first application of the technology. So we'll try to be pretty objective on that. What are the expected advantages, but also what are the challenges and issues that we see, at least from an international perspective. I think that is also important to provide a short overview of the activities and services that the IAEA can provide to the interested member states. In that, we'll try to encompass not only the services from our sub-program, but also from the rest of the Department of Nuclear Energy, and also from other departments, in particular the Department of Nuclear Safety and Security, and also the Department of Nuclear Safeguard, which are becoming very, very active on the sector and trying to address the many requests from the increasing requests from member states. So let's have a look first at the situation of nuclear power in the nuclear power capacity in the world. As of today, there are really fresh data from our PRIS database. So we have 442 nuclear power reactors operable in 31 countries, with the Barak Unit 1 in the Emirates came online in August, so is the newcomer. The corresponding overall net installed capacity is somehow almost 400 gigawatts. And what is new is that there are 53 nuclear power reactors under construction in 19 countries, corresponding to some 56 gigawatts of total capacities. The distribution in the different regions of the world is reported in the lower part of the slide. And well, the message is very clear that the Far East Asia slowly is taking over in terms of nuclear power capacity. They are really more or less already at the same level of Western Europe and North America, and it is supposed to overcome these two regions of the world very soon, in coming, let's say, in this decade. So the trend is clear. Asia is becoming the main player as far as nuclear power program and capacity. Of your possible interest is, of course, what is going on the countries which are new in the nuclear sector, the so-called newcomer countries. As I said, there are 53 nuclear power reactors in 19 countries. Some of them, of course, they are very experienced nuclear countries, like Russia, India, or South Korea, and obviously China. But there are also some newcomer countries, which maybe represent also, to some extent, some reference, some example for you. So, as I said, the Emirates have connected their first APR 1400 to the grid in August, and now they are very close to completion of the other 3 units. Then we have Belarus, which is another very advanced newcomer countries, where they have already uploaded the fuel in one of their VVR 1200. And then we have Bangladesh and Turkey that they are more or less at the same level with the other, I mean, each units. Sorry, sometimes very strong noise. Okay, thank you. So I said Bangladesh and Turkey, they have other 2, each of them, they have 2 units of VVR 1200 under construction. And then there are other, well, I would say more than potential embarking countries, because they are already, they have expressed a bigger commitment in building nuclear power plant, and these are Egypt with a big agreement with the Russian Federation for potential 4 units of BVR 1200, and then we have Saudi Arabia, which is in the process to launch a bids to vendor countries for 2 units, and then with a very ambitious target of 16 gigawatts at the horizon of 2030. So when we talk about this, let's say, current status and above all, new nuclear installation, what are the technology we are talking about? But they are all large, so-called large advanced PWR and BWR, which are already available in the market. They are, I mean, they can be ordered. And here are the 6 vendor countries with their offer in terms of large water reactor, which have an installed capacity ranging from 1 gigawatt to 1.5 and even now some 1.7 gigawatts. So they are very big guy, which of course they require a big effort from the countries that they want to adopt this technology. And we know that, well, it's a matter of fact that at least in some region of the world, the construction of this big nuclear power plant, which are relying heavily, of course, on the economy of scale, in some cases have posed a problem in terms of longer construction times due to several factors, the complexity of the design, the problem related to the supply chain, the fact that all of these new reactors in the different part of the globe were first of a kind. So we know that it was the same also for the Gen 2 reactors. Of course, when we talk about the first-of-a-kind reactors, there are also unknown, there are also unexpected problems. And however, the world is not homogeneous from this point of view. And as you can see from this graph, in terms of capital cost per kilowatt, the situation is pretty different in Asia and in Europe. In Europe, fortunately, we have observed that there have been projects not really on time and on budget. From this construction, of course, there is now construction of first-of-a-kind reactors. There is, of course, a big lesson learned. And here we have summarized, let's say, what should be the key success factors. As I said, the fact that, of course, it is very important to rely on a robust supply chain, to rely possibly on a proven technology, to have a close cooperation engagement with the regulator in the very early phase of the program, and then of course lesson learned also from other countries which were particularly successful in the realization of these Gen 3 reactors. So there is a good lesson learned, and of course there is now expectation that the nth of a kind will be constructed on time and on budget. But it remains true that this, as I said, this big construction require a big effort from a country, in particularly from newcomer countries and not very well developed economy. So at a certain moment, the nuclear community posed the question that maybe it's we have to consider also some, let's say, change in the game. Okay, at least tried to offer another product. Which is not intended to replace the large advanced water-cooled reactor, but can open the door of the nuclear power deployment to countries that are not in the position, for different reasons, are not in the position to afford these large water reactors, both in terms, for instance, of financial implication, or because they don't have a grid particularly developed, or because they represent, I mean, part of the world, remote regions of the world, for which, of course, is difficult to install I don't know, several gigawatts electrical. So this game changer is represented by the so-called small modular reactor that the agency defined as advanced reactor with a typical capacity of 300 megawatt electrical. One of the let's say game changer is the fact that they are supposed to be built in factories instead of on site. So favoring, of course, the concept of modularization, and also trying to speed up the time for construction. And then when these modules are ready to be delivered by the factory, are transported to the site and installed on site according to the demand. So since they also apply this modular concept, they can adopt a staged approach in terms of installation. A country can, for instance, think to order only a few modules according to the need of today, of the capacity needed in terms of capacity of today, and then add new modules according to the raising in the demand. So this is clearly a concept which in principle demonstrate one of the main flexibility of this technology. The other point is that since they are a small module, up to each module up to 300 megawatt electrical, they should be more affordable for the financial viewpoint, even though, of course, they cannot rely on the economy of scale. So if the cost of kilowatt hour will be competitive, is still to be demonstrated. But for sure, if we consider the absolute let's say cost of the reactor, since the reactor is smaller, also the financial implications are not so demanding like in the case of large water reactor. The other flexibility is that they are very good. We will try to explain why, but they are particularly suitable for different applications. So not only for power application for electricity production, but also, for instance, to generate heat for various industrial applications, for desalination, for hydrogen production. And they are also flexible in the sense that they may be the right choice also for remote regions and for grids which are not particularly developed. In terms of course, they are also supposed to contribute to reduce the CO2 footprint of the world, because, for instance, they are suitable to replace aging fossil fire plants. There are a number of coal plants in the world which have a capacity around the same that we have said, around the 200-300 megawatt electrical. So, of course, if we are able to replace these old coal plants with the SMR, for sure, we will reduce significantly the CO2 equivalent emission in the atmosphere, and so contributing to mitigate the problem related to the climate change. Finally, they are so flexible that they can be integrated with the renewables. So we know that in many parts of the world there is an increasing introduction of these variable renewables, which poses some problem in the managing of the grid. Well, the perfect integration seems to be with SMR because of their flexibility and because they don't produce CO2 like renewables. So if we wanted to have a perfect system which generates several energy products in a very clean way, well, the integration between nuclear power and renewables seem really very promising. I also want to point out the fact that, well, in recent years, we have seen also an increasing interest for so-called microreactors, which are, let's say, a subset of the SMR, typically with a power of not above 10 megawatt electrical. And for instance, they are considered for many applications, also to replace diesel generators in small islands or remote regions. And of course, in case you have a limited grid with a significant, let's say, deployment of variable renewables, even in this case, we have the possibility to back up the renewables with a clean energy source of the right capacity. So let me go quickly to the, let's say, to describe, but very briefly and without technical detail, the main design characteristics of this SMR. On your top left, you can see a typical, well, a comparison actually between a typical four-loop pressurized water reactor with all the, which also show the different components, the reactor pressure vessel, the four generators, the pumps, and the pressurizer. What is the main concept on an integrated PWR, which seems to be now the technology of interest for Indonesia, is the fact that there is a possibility to make a very compact design by integrating all the main components, so steam generators, pumps, pressurized, in some cases even the control rod mechanism, into the reactor pressure vessel. In this way, the whole nuclear island becomes particularly compact. Of course, as usual, there are drawbacks, because if you put all the main components inside the reactor pressure vessel, it's clear that the RPV becomes bigger and also taller. And since there are, of course, mechanical consequences and stress, etc., it means that there is also a limit in the max power of the reactor, above all when we then also pretend to transport this reactor as a module, so were fabricated and then moved to the side. And when we move this module to the side, normally their layout is the one showed in the top right part of the slide, where we have.
Sorry, Mr. Monti.
Yes. Sorry.
I'm sorry. I'm sorry to interrupt you, Mr. Monti. I'm sorry to interrupt you. Yes. The minister will have to attend another event, and he would like to leave now. So we would like to. Yes. Thank you. So, Minister, thank you so much for your keynote speech today, and for attending the event, and for giving us encouragement to work harder and make sure that we have a clear path toward our nuclear power program. On behalf of the National Nuclear Energy Agency, we thank you for your participation, and I understand that your team will still be with us, and we look forward to further discussion with the Ministry of Research and Technology after the webinar. Thank you, Minister.
Thank you very much, and good evening. Please let me know when I can go ahead, please.
Yes, okay. You can start now. Thank you.
Thank you. So
you can begin again.
Okay, I will restart my presentation from the point
I'm sorry, Monty. Yes, you can start again.
Okay, so I hope that you can still hear me clearly. So we were describing a little bit the main features of this SMR, realized in a workshop as a module, and then brought to the site, and then placed in this layout, in a multi-module layout configuration, which allows to, let's say, meet the demand just by adding modules according to the needs. As I said, the overall plant, the overall nuclear island becomes particularly compact with the adoption of this integrated system. And so this SMR may be also suitable for underground construction, of course, with positive consequences in terms of security and resistant to seismic events. The other main feature, which is, let's say, common to all the SMR being considered today, so the advanced SMR, is that they heavily rely on passive safety system. Okay, so on that, there are expectations that we can have an enhanced safety performance. For instance, a more benign behavior in terms of design extension condition, let's say in the most severe accident condition. Even though, of course, they rely on natural, let's say, on natural phenomena, but this can be also be challenging in some situation, in order to demonstrate that they are reliable and they perform efficiently as requested in any scenario. So if we consider the case of IPWR, we can see clearly, just from the point of view of safety, clear advantages, but for each advantage there are also things that is not necessarily a problem, but is something which requires some specific demonstration. Let's take the case of, for instance, that we were just discussing, of the wide use of passive safety system. So that, which is an advantage, because it means that they can operate without an external electrical supply. But since they rely on natural circulation, of course, you have a lower driving heads. So, of course, you have to demonstrate that the system is reliable in any normal or abnormal situation. Another point that I can mention, say that they are integral PWR. So in this way, of course, you eliminate all the large piping typical of a loop-based pressurized water reactor. So in this way, you should exclude by design the large loca. But of course, there is an increased number of small piping connected to the RPV, and of course, you have to assure that they don't break, and then also what are the possible consequences of the so-called small breaking lock. So as you say, I don't want to go into all the details. You can see yourself. There are also, from the safety viewpoint, there are clearly advantages, but there are also some issues that sometimes they also require some experimental validation through tests in order to support the safety case. So let's have a look now to the technology holder. Since you are a potential buyer country, of course, you would like to know who is going to offer SMR worldwide. As you can see, there are 16 countries in this moment which are considered technology holder. Well, I put also Indonesia because of the small RDE that you have been developing in recent years, the small high temperature gas-cooled reactor. And then, as you can see, there are almost all the major players of the nuclear power sector in the world. As I said, yes, we can say that we have also two embarking countries which somehow can be considered technology holder because, for instance, they have signed some joint venture with other well-known vendor in order to develop and then deploy some SMR concepts. What are the nowadays we have more than 70 SMR design around the world proposed. Of course, they are at very different stage of development. We range from one SMR already producing electricity and heat up to concepts which are really at a conceptual stage. So, you know, in terms of potential for deployment, the situation is very different, even for the different technology. And the range is very, when we talk about nuclear power plant, the range depending on the status of development, is very significant. It is between a few years and several decades. So, of course, to well understand the status, the real status of development of a technology is really key for a country which is thinking to SMR for, let's say, a near-term deployment. However, it's very well known that we have three front runners. One SMR is in operation. I'm talking about the KLT-40S in Russian Federation, which is budget mounted on the very famous academic Lomonosov. We have the HTR-PM, high temperature gas cooled reactor in China, modular HTR, which should start operation next year. And then we have KAREM, which is the IPWR closer to deployment in Argentina, and is supposed to start operation in Argentina in 2023. And then we have, as I said, a very large variety of different technology, from land-based water-cooled reactors to micro-reactors to even fast reactors, high-temperature gas-cooled reactor, marine-based water-cooled reactors like KLT40S, and also molten salt reactor. I think that this is one of the most interesting slide for you. It shows the capacity of the megawatt electric, installed megawatt electric per module of the, let's say, near-term deployment SMR versus the time of deployment. So as I said, we have KLT40S already producing electricity, connected to the grid in 2019. Then we have the gas-cooled reactor technology, the modular gas-cooled reactor technology in China, expected to go operational in 2021. The KAREM, the IPWR KAREM in Argentina in 2023. And then we have other concepts, both other PWR, IPWR, even fast reactor like Brest 300, which according to the vendor's claim should be available around mid of this decade. And then we have a number of reactors, some of them even under licensing, of that they have completed their certification, which are supposed to be available, commercially available, at the end of this decade. I want to just to mention some of them: the SMR 160, the SMART, developed by Korea with Saudi Arabia, the new scale in US. I think that there will be a specific presentation. If we look at the, if we suppose that this is true, that all these reactors will be connected to the grid, will be, at least will start producing electricity in this decade, overall, in the most optimistic scenario, we are talking about 1.6 gigawatt electrical of installed capacity by 2030, by the end of this decade, which is equivalent to 1 unit of a French EPR. So if we are honest, and according to the reality, we don't see a large deployment of SMR, at least in this decade. The big deployment, the real breakthrough, is expected in the next decade, where most probably there will be a large number of, maybe not 70, but a large number of SMR available. There are also expectations that they can really produce in series like aircraft. So of course also the let's say the time of construction of the single unit should be much shorter than a large reactor. So in terms of installed capacity and in particular also contribution to the CO2 reduction, from our perspective, this is realistic to be seen only in the next decade. And then, of course, there are expectations in coming years and decades. I also wanted to point out to this particularly interesting aspect of SMR, which on one side is the so-called flexibility, which we have mentioned many times, and on the other side, the fact that they are very good for different, let's say, non-electric application, in particular for hydrogen production, which means really to contribute to the clean energy transition, not only in the power sector, but also in the transportation sector. And we know that for the hydrogen revolution to take place, hydrogen must be generated from non-fossil sources, but also at a price which should be competitive with cheap oil. Okay, only in this case we will have on one side the possibility really to introduce the hydrogen economy and in a clean way. Okay, because if we continue to generate hydrogen, for instance, with gas reforming, we will have always to manage the problem of where to put the CO2. So, and just from this point of view, I would like to give you some interesting numbers from the, let's say, investment viewpoint. I've recently read a very authoritative document, which was stating that in order to achieve, let's say, to transit to the hydrogen economy in, let's say, in a 30 years time frame, there is the need of a global investment of 17 USD trillions. So the industry should spend, if we wanted to transit using both renewables and nuclear power plant, we wanted to transit to the hydrogen based fuels, we need an investment of around 17 trillions US dollars, which has to be compared with the announced 25 trillions of investment that oil and gas industry expected to spend in the same period to maintain a reliable fossil fuel flow. And this is dramatically less than the estimated 70 trillions of US dollars in investment that would be necessary for an equivalent hydrogen strategy, but based only on wind and solar. And as I said, we wanted to transit to a clean energy system in an affordable way. So, of course, SMR, which are particularly suitable for this application, are a real breakthrough, even to assure a transition, a clean energy transition to the non-electrical sector. And finally, they are very flexible, as said, and flexibility, as reminded recently by Faith Birol, the executive director of the International Energy Agency, is really the magic word of the energy sector for the years to come. So here, on the basis of all this discussion, we have summarized the advantage, but also the what we see as issues and challenges of SMR. I don't repeat the advantages because I've elaborated on that enough. I just wanted to point out some technology and non-technology issues. The fact that we don't have operational experience of SMR and we don't have a consolidated supply chain for multi-modules is an issue. Is an issue that the industry, of course, is called to address as soon as possible and according to the time to deployment. So, of course, also the, let's say, the experience on operation and maintenance is very important. Also, the overall, when we talk about the non-technology issues, we have also to demonstrate the economic competitiveness of these reactors, and not only with respect to the large water reactor, which can rely on the economy of scale, but also with other energy sources, and including the fossil fuel, because the real transition, as I already mentioned, the real transition to a clean energy system will be possible even only if the energy sector will demonstrate to be competitive with respect to the current way to produce electricity and other energy forms. Now, quickly going through what the IEA can offer to the member states in terms of activities and services. Well, first of all, I think that we are known worldwide because every 2 weeks, 2 years, We produce this booklet. We have just published the 2020 edition of this Advances in Small Modular Reactor Technology Developments. Let me point out that this year, this booklet is really comprehensive in terms of all the different SMR technologies being considered worldwide. You can see here the full list. We have also introduced a chapter on microreactors and even on test reactors. And last but not least, I want to point out that for the first time, we have also included some information regarding fuel cycle, decommissioning, and final disposal. Yes?
Mr.
Please.
Monti, I'm sorry, your time actually is up.
Okay.
Can you finish your presentation? 2 minutes? Thank you.
I will do. Thank you. Sorry. I want to also to mention another important service provided by the IA. Again, it should be of interest of Indonesia, which is this reactor technology assessment, a methodology to compare different reactor technology. And the big news is that we have revised this recently, this methodology to include also the case of SMR and also non-electrical application. In coming months, this nuclear energy series will be published as a new revision, also with an IT tool which is very useful for comparing the different SMR available in the market. And in parallel, we will be able also to publish this technology roadmap that, in our view, is another very interesting tool for the embarking countries. First of all, because it gives a pretty objective status of deployment of SMR. It really addresses all the infrastructure development, what is needed in terms of associated infrastructure, not only to build the reactor, but to conduct and manage the whole nuclear program. And then it offers different roadmaps, which can be adapted, of course, roadmaps to deployment, which can be adapted to the different needs of member states. The last word is that I spend concern safety. One of the issue and one of the big expectation also for public acceptability of SMR is the possibility to reduce the emergency planning zone. This key also to propose SMR as a possible replacement of aging fossil fuel plant, even because of public acceptability. Well, there is a room to really dramatically reduce the EPZ in case of SMR, under one condition, that we have a less prescriptive approach from the safety viewpoint, a more risk-informed approach. And it means that we should start to look at this nuclear power plant in terms of environmental impact in case of accident, taking into account the technical characteristic of SMR. So it means that we take into account that SMR have a much smaller, obviously, much smaller source term than larger reactors. And this SMR, they heavily rely on a passive safety system. So applying, of course, correctly the PSA, we can demonstrate that the probability of larger release around the site is much less, because of some events can be excluded. To address this possibility, the Department of Nuclear Energy, my section, in collaboration with the Department of Nuclear Safety and Security, has launched this coordinated research project, which also Indonesia is a partner, which is very well advanced. We had a very promising, let's say, virtual meeting held in September 2020. We plan to complete this CRP next year, and I'm sure that some outcome of the CRP will be really very interesting to create let's say, the technical basis for development of safety standards, which can address the EPR and EPZ.
Mr. Monti,
I've completed. Sorry. I've completed
Yes,
my
thank you.
presentation.
Thank you, please. Okay, thank you very much.
Welcome.
Now, yes, thank you so much for the overview. You have actually a comprehensive slides, the one that we see. I'm sure that this is very beneficial for us. We will share it with the participants immediately. Thank you. And for the vendor, we will start with our first speaker from the vendor, Ms. Cheryl Collins from NewScale Power. Ms. Collins is a Director of Sales and Business Development at NewScale Power. She previously served as Director of Fuel Cycle Business Development for Westinghouse Electric Company. She has diverse experience in management roles, also at GE Hitachi Nuclear Energy and Global Nuclear Fuel. Ms. Collins, you have 15 minutes to deliver your presentation. I give you the floor.
I cannot share my screen until the other participant stops sharing his screen.
Please, Mr. Monty, stop your sharing. Okay, you can start now, Ms. Collins.
Okay, can you see my screen?
Yes.
Continue,
All right,
please.
well, Ms. Johanna, thank you so much for the kind introduction and for allowing NewScale Power this opportunity to present on and participate in today's session on the technology and the safety of SMRs. I would like to acknowledge that NewScale has received financial assistance via competitive bid process from the US Department of Energy. And so the views that I present today in this presentation are my own and not that of the department. So at NewScale Power, our mission is to provide scalable advanced nuclear technologies for the production of electricity, heat, and clean water to improve the quality of life for people around the world. And we do this by providing energy that is smarter, cleaner, safer, and cost competitive. Our technology provides high capacity, reliable baseload energy that is not found in operating nuclear power plants today. So for those of you that are not familiar with NewScale Power, let me just share a bit about NewScale Power with you. The concept originated in 2000 with a funding from the US Department of Energy via the MASLAW program, which is the Multi-Application Small Light Water Reactor program. Then in 2007, Dr. Jose Reyes formed NewScale Power for the sole purpose of completing the design and taking it to commercialization. Well, the program really did not take off until a couple of things happened. One is Fluor, who is the global engineering and construction company, became our lead investor in 2011. And then in 2013, NewScale won a competitive US DOE funding opportunity. And to date, this program has dispersed over $300 million towards this technology design. So today, I am proud to announce that NewScale Design has completed its rigorous design review by the US Nuclear Regulatory Commission. We received the NRC's final design approval last month. We've got over $1 billion in investment in NuScale to date, and we are readying our technology for manufacturing and construction. So let me talk a little bit about the core technology. So the core technology is a fully fabricated small modular reactor that we call the NuScale Power Module. So this module includes the reactor vessel, the steam generators, which is contained in the reactor pressure vessel, the pressurizer, and the reactor core. And then this reactor pressure vessel is surrounded by a high containment stainless steel, high pressure stainless steel containment vessel. Each module delivers 60 megawatts of electricity at the turbine generator. They're small enough that they can be factory built and transported for installation in the at the reactor sites. The NuScale power plant has 12 of these modules delivering 720 megawatts of electricity for a total gross output. As I mentioned, there are 12 modules in the NuScale power plant. As you can see, that each of these modules is dedicated and is connected to a dedicated power conversion system. This is a fully factory fabricated, skid mounted turbine generator, the condenser, and the feed and condensate equipment. So each module feeds one turbine generator and it eliminates the single shaft failure, which means if one turbine generator fails, the remaining 11 modules in the power plant will continue running and generating electricity. Also of importance is that these modules can be incrementally added to match the growth or the economic needs of the facility, and we can run from 1 up to 12 modules installed. The NuScale power module design is simple, and therefore simplicity enhances safety. The design is based on natural convection for cooling. So it's driven by gravity and natural circulation over the fuel. There is no pumps, no emergency generators. As you can see, the design is second to none on the safety case. And this enables a site boundary emergency planning zone for our technology. So in terms of safety, we have what we define as the indefinite coping period. Well, what does this mean? Let me just explain with respect to the Fukushima event. So the earthquakes shut down the reactors, and they shut down automatically, which is what they were supposed to do. The facilities then went on backup power provided by the diesel generators. But then came the tsunami, and the tsunami caused the diesel generators to shut down. So when the stations had lost all power, they had a certain amount of what we call coping time, and in this case, 72 hours to do something. They had to either start the pumps, open the valves, or add more water into the reactor to keep the reactor cores cool. When this failed to happen, the reactor cores overheated. Well, in our design, all our modules are sitting in a pool of water. It's 7 million gallons of water that they're sitting in. And so on the loss of power, our modules would automatically shut down and will self-cool for an indefinite period without the need to add any water, no need to start the pumps, no need for external power. So the reactors continue, the modules rather sit in the pool of water and they reject heat, decay heat that is generated into the pool of water. Over 30 days, the water boils off, and as you can see in this graph, the amount of residual heat that's left after 30 days is enough that the natural air circulation can remove the residual heat. So I want to talk about a new approach to construction and operation. All the modules are factory fabricated in parallel as the construction is ongoing for the reactor building and the balance of plant at the reactor site. The modules are then transported, shipped via truck, rail, or barge to the construction site. There is no field fabrication or construction associated with these NuScale power modules. This drastically, as you can imagine, that this will drastically reduce the construction time. And of course, due to factory fabrication, you would have an improvement on the cost because of repetitive fabrication as compared to the large nuclear power plants. So the NuScale module of the power plant is designed to go beyond base load. The plant provides electricity, and it can also provide heat for desalination, for hydrogen production, and for heat for oil refineries for the industries. I think it's important to note that the modularity and the flexible nature of our design allows us to extensively load follow with renewables. So we are a complement to wind and solar, and we can maneuver either quickly with quick responses, dumping the steam to the condenser, hourly changes using control rod blade maneuvers, or for extended periods of load demand changes to take one or more modules offline. So we can respond rapidly or as needed to the demands from renewable energy. We've studied all these different capabilities, and we've published papers on them. This is what we call NuScale's diverse energy platform. This particular slide highlights the new level of plant resiliency that you will find with our SMR. Especially for hospitals, mission critical facilities like the hospitals, the data centers, the national defense facilities. This plant has several capabilities, and that includes a black start island mode operation followed by the loss of power, offsite power, with the first responder power when needed. We provide resilience to natural events like the earthquakes, tsunamis, and to aircraft impacts because the modules and the reactor are located below grade in a seismic category 1 building. Our control systems are protected and not vulnerable to cybersecurity issues. And then finally, the plant is resilient to solar-induced geomagnetic disturbances and electromagnetic pulses. We've covered the technology and the safety aspects of the NuScale SMR. I'd like to move on to discussing the progress in licensing, supply chain, and our customers. So as you can see, it's taken us a long time to get here. When I mentioned we started the concept in 2000 and NuScale Power was formed in 2007. We've invested over $1 billion in development of our technology. The most recent milestone, which we're extremely proud of, is NRC's, the U.S. Nuclear Regulatory Commission's approval of our design. And we will complete the standard plant design. We will start the first forgings and start the module fabrication in 2022. And these are the milestones that are listed in this mountain of commercialization activities that we will be seeing in the near future. As I mentioned, we are the first SMR in the United States to undergo licensing, and we have just announced in August 2020 that the US Regulatory Commission completed phase 6 review. This is the last and final phase of the design certification application for our reactor. And the NRC has issued a final safety evaluation report. And what that means is that customers can now proceed to develop new scale power plants with the understanding that the NRC has approved the safety aspects of the new scale design. So with the design approval behind us, we are now focused on our supply chain. We're working with BWXT Technologies and our partner, Doosan Heavy Industries. We're actively engaged in completing the design so we can manufacture the assembly and the transport, understand the transport of the new scale power module itself. We have several manufacturing trial activities that have commenced recently. I would also like to highlight that we have received the American Society of Mechanical Engineers. This is the N certificate of authorization, which is typically referred to as the N stamp certification. And this enables NuScale to certify and apply a certification mark to our SMR, signifying that this design is constructed and in accordance to the ASME codes. So this slide essentially shows you the prototypical demonstrations that we've undertaken by some of our program partners. As you can see, Doosan is working to improve the processes that will be used to manufacture the new scale power modules. Here's another slide that shows some of the work that's ongoing with the instrumentation controls, and that is the distributive controls, and the work that is ongoing with the refueling and the remote handling equipment. So from a customer front, our first customer is the Utah Associated Municipal Power Systems. They provide energy services to community-based power systems in 7 Western states. So UAM's made a decision that they are going to replace their retiring coal generation with a 12-module, 720 megawatt NuScale power plant. And this will complement their renewables portfolio. This first, they call it the carbon-free power plant project. This first power plant project will be deployed at DOE's Idaho National Laboratory site. As with any project, the main question is, what is the cost? And the cost is a consideration. This slide shows you the first of a kind cost and the nth of a kind cost. This is the overnight cost of capital for a plant that is going to be built in the US. And this cost references a plant to be built in the southeastern part of the US using a greenfield site with US labor and US productivity. Originally, these costs were rolled up. The original estimate was in 2014. We updated it in 2017. So these costs are in 2017 dollars. The estimate complies with the American Association of Cost Engineering International Class 4 estimate. It excludes warranties, contingencies, fees. It also excludes owner costs, escalations, because this cost is very location, country, and site specific. We believe that this cost is highly competitive with current gigawatt size reactors. And we're currently finalizing and developing a class 3 estimate that will contain location specific costing elements in the United States. So a near-term focus is trying to get our first plant deployed in the United States. And we continue to engage several customers in the United States, especially in states that have legislation passed for greenhouse gas emissions reductions. On a global perspective, as you can see here, we have a lot of customer interest on our technology, especially as our technology nears commercialization. The foreign governments and utilities see NuScale as a viable near-term solution for meeting their energy needs, and especially water needs, clean water needs, and meeting their carbon emission goals. We've signed agreements in Canada, Romania, the Czech Republic, and several other countries. And in Canada, we've actually submitted the phase 1 and phase 2 of our pre-licensing vendor design review to the Canadian Nuclear Safety Commission. I firmly believe that the SMRs are the future of energy. After over a decade of research and development, testing, licensing, and engineering, the NuScale SMR is closer to commercialization. We're delighted to embark on this journey with our first customer, UAMPS, and with program partners like Doosan. We're confident that our first project will be the catalyst of many more projects to come in the United States and throughout the world, and certainly in Indonesia. Thank you very much.
Thank you, Ms. Collins. Okay. Thank you so much for the presentation. You cover the safety aspect, the design, the technology readiness, and also the cost and the cooperation that you're working on with others. So, okay. So our next speaker is Mr. Anton Moskvin from Rosatom Overseas. Mr. Moskvin is a Vice President of Marketing and Business Development at Rosatom Overseas. And he has over 10 years of professional experience in the Russian nuclear energy industry. Currently based in Moscow, Mr. Moskvin leads Rosatom Overseas activities in international business development, scouting for market opportunities, and promoting the Russian nuclear technologies abroad. Yes, so you have 15 minutes to deliver your presentation, Mr. Moskvin.
Your Excellency, thank you very much, dear colleagues. It's a great pleasure for me to participate in today's conference. Do you see the presentation on the screen?
Yes, sir.
Yeah, that's fine. Okay, thank you. First of all, me personally and the whole international team of Rosatom, we strongly believe in the development of nuclear power in Indonesia, and I think Indonesia has all it takes to launch one of the strongest nuclear power programs in the region. I've been myself several times to Indonesia, and I'm glad to participate in today's conference. Let me start with the brief introduction of Rosatom. We are one of the leading nuclear technology companies in the world. Our main area of competence is design, construction, and operation of nuclear power plants. We are the only nuclear vendor in the world to offer the full range of products and services across the whole life cycle of the nuclear power plant. And one of the strongest assets of our company is nuclear power plants construction competence. We have never stopped constructing the nuclear power plants and developed our designs accordingly. Through recent 14 years, we have launched 15 new nuclear power plants in Russia and in foreign countries. And at the same time, we are the largest utility in Russia. We have 25 gigawatts of nuclear capacity operated at 31 units. We do believe that the advantages of small modular reactors are very important nowadays. They have their unique benefits to gain a considerable share of the new nuclear power plants market. And since 1954, we have designed and manufactured over 20 small reactors, both for civil and marine applications. We have accumulated vast experience in operation of small reactors for icebreakers fleet, over 400 reactor years all in all. We are renewing our icebreakers fleet. You can see one of them on the slide. With the new class, that would be even more powerful and effective than the existing ones. These icebreakers based on written 200 series SMRs, and they will have the variable draft and will be able to navigate both shallow rivers and the deep seas. 6 written 200 reactors have already been manufactured and installed on universal icebreakers of this kind, and 2 of them attained criticality in November 2019. The first icebreaker of this type will be commissioned this year. And based on this vast experience, we developed the world's first floating nuclear power plant, Academic Lomonosov. Mr. Monti described that in his presentation. It has the electric capacity of 77 megawatt, enough for large industrial facility or a small city with a population of more than 50,000 people. It produces heat along with the electricity as the climate of the region is very cold. And in September 2019, the unit transportation was successfully carried out. We covered almost 5,000 kilometers within 17 days till its destination. And in May 2020, it was commissioned and is currently operating safely. With all these historical facts, now let me introduce you our next big step. Our most modern design of a small modular reactor, it's written 200, an evolutionary technology development based on its predecessors and incorporated all our experience of SMR's designs, construction, and operation. It is the time-proven PWR technology. It has integral design with the steam generators located inside the reactor vessel. It is referenced in manufacturing. It's not only pictures and even drawings. 6 of them have already been manufactured and installed on the icebreakers. Written 200 features integral design. One important aspect of our integral design is that it almost eliminates the classic large loss of coolant accident and makes the reactor very compact. It has 4 steam generators. Steam temperature is average 295 degrees Celsius at 3.82 megapascals and capacity of 261 tons per hour. We use 4 more main circulation pumps. Why? We performed numerous studies and came up to the conclusion that forced circulation leads to more stable performance. All key components of the reactors are referenced. Major equipment is similar to that used at KLT-40S at our current floating nuclear power plant. So we can say this is a tested innovation. The height of the core is 1.6 meter. We use 199 fuel assemblies, 12 control rods, and 6 safety rods. And the fuel is low enriched, and the reactor is quite maneuverable. You can see that power change rate is 0.1% per second. Now let's talk about safety. Rosatom SMRs ensure nuclear and radiation safety and guarantee resistance against different external events. It is done in full compliance to the strictest regulatory rules and post-Fukushima requirements. Safety is enhanced by combination of redundant and separated set of active and passive systems, inherent safety features, defense in depth principle, And basically, there are three functions that any reactor of our design has to perform and to ensure its safety. We need to cool the core. Active and passive safety systems excellently perform this. We need to control reactivity. To do that, we have 6 groups of safety rods for fast shutdown, less than a second, 12 groups of control rods, and maintain the reactor in shutdown state. We need to localize the radioactive material in case of accident development, and our in-vessel retention system provides for that. In case of an unlikely accident, for example, total station blackout or LOCA, the reactor will stay safe for an unlimited time till the core is cooled enough. And in even more unlikely accident case, for example, of 2 emergencies happening together, LOCA plus total station blackout, my colleagues from the engineering team have provided 72 hours grace period, which is definitely enough for safety strategy implementation. And in addition, one more really strong barrier which we developed is the accident-tolerant fuel cladding that almost eliminates the possibility of hydrogen explosion. So the SMR is resilient to various internal and external events like extreme temperatures, tornadoes, wind loads, earthquakes, and it is also able to withstand aircraft crash impact. There are 2 small NPPs options available, floating and land-based. They are both based on Rhythm 200 series SMRs, and I will give you more details about the floating NPP first shortly. The floating NPP combines the traditional advantages of nuclear power with its unique benefits such as short period of construction works on site. We have long fuel campaign. It's absolutely unique on the market. It's up to 10 years. No decommissioning on the site. We will take the plant back to Russia. Flexible lifetime period. The floating nuclear power plants are built from start to finish in shipyards, and we presume mass production of FNPPs and therefore more efficient construction. In addition to cost savings, the FNPPs are very flexible and can be transported to another site. Compared to academic Lomonosov, the new FNPP is more compact, more powerful, and more efficient. The electrical capacity is 200 megawatt. We increased fuel cycle to 10 years and the design life to 60. We have already completed the concept design of the FNPP and plan to move the technical design stage by the end of this year. Now a few words about the land-based energy solution. We have developed the concept design of our land-based SMR. It is equipped with 2 Rhythm 200N reactors with an overall installed capacity of 106 megawatt. It has design lifetime of 60 years and the refueling cycle is also quite exclusive, up to 6 years. The capacity factor exceeds 90%. Speaking about the construction time, we expect it to be around 4 years for first of a kind, and we plan to decrease it to 3 years for next of a kind. And Rosatom SMR allows a high degree of flexibility to direct the heat output for either electricity production or district heating. It can be deployed near residential areas or industrial facilities due to the emergency planning zone limited to the territory of the NPP. The design is modular, which makes Rosatom SMR a suitable solution for local energy needs. Modular construction allows increasing power generation by step of 106 megawatt, and the auxiliary buildings area stay in shared use for all new nuclear units. Speaking about the site characteristics, it's important to point out that our SMR is well protected against earthquakes. The design of the station allows to withstand peak acceleration of up to 0.3 G. However, the reactor itself is able to withstand up to 3 G acceleration. Special notice was taken to the transportability of the key components of the station. The heaviest component is the reactor vessel with the weight of 146 tons and the dimensions indicated on the slide. The reactor vessel is transported separately in a specially manufactured carriage for railway or road transportation. The other equipment may be transported by usual means of transport. And here you can see some real pictures of the transportation of written 200 RPV by railway in Russia. Now let me share with you our approach to the price estimation. We design our SMRs taking into account the target commercial parameters that should ensure its competitiveness compared with the conventional generation sources like coal or gas. On the other hand, the particular cost of SMR varies greatly depending on the financial aspects of the specific project. And first of all, I'm speaking about the cost of financing, which greatly depends on the model of project implementation and local economic situation of the project implementing country. The large effect of the discount rate is clearly visible on the slide. But in addition to particular costs of the SMR and PP project can be determined precisely and may vary depending on site parameters, regulatory requirements, construction conditions, nuclear power plant configuration, and some others. This is just like for the large nuclear power plants. We in Rosatom follow the policy to offer only a reference solution to our potential customers. Here I would like to quote Director General of Rosatom, Mr. Likachov. He said that an important aspect of our foreign practices is that Rosatom always follows the principle. Firstly, we build in our own country and only then offer technology to the foreign markets. So we are now focused on our first-of-a-kind project in Russia. Rosatom is considering several sites for the first land-based small modular reactor in Russia. We do not have design certificate stage in Russia, so we are getting prepared to get the site license by 2023, to license for the construction by 2024, and we are planning to start the construction same year. The major target year is 2027, and we plan to commission this when we plan to commission the SMR. Through all our international projects, we guarantee the widest involvement of local engineering and construction companies. Local vendors have chances to provide general construction and installation services, supply machinery, materials that do not affect overall safety of the nuclear plant. If the local industry is advanced, then local input will be definitely higher. Summarizing what's been said, let me reiterate some main takeaways. First, we have strong experience in design, construction, and even operation of the small modular reactors. Our latest projects are the floating nuclear power plant Academic Lomonosov, commissioned in May this year, and 6th generation 3+ Riton 200 reactors manufactured and installed on the icebreakers. What's important about our market proposal is that we always test and try the nuclear power plants in Russia before offering them to our international customers. And in case of the Riton 200s, they will be tested in the most severe technical and environmental conditions of the icebreakers. Riton series SMRs feature a time-proven PWR technology with an exclusive fuel cycles of up to 10 years and an accident-tolerant fuel. Riton series SMR is safe. Safety is enhanced by combination of active and passive systems. And land-based SMR and PP project in Russia is already being implemented, and in 2027, the nuclear power plant is going to be commissioned. To conclude, let me reaffirm that Indonesia is one of the most important and interesting partners for Rosatom. We are ready to provide all the required support to the development of your national nuclear program. We are sure that both large-scale NPPs and small modular reactors may find their place in your energy system and strengthen the country's economy, education, science, and high-tech industries. We are open to any kind of project implementation models, by the way, ready to invest into the capital of the nuclear power plants, ready to share knowledge on the project planning, construction, and operation. And as I said in the beginning, Indonesia has all it takes to launch a strong nuclear program, and we are ready to assist. Thank you very much.
Okay, thank you very much, Mr. Moskvin. Thank you. So your presentation covered the readiness of your technology, which can be deployed potentially in 2028 and beyond. So our next speaker is Mr. Han Ok Kang from Kairi, Korea. He is the Director of Smart Project Management, and he began the smart development quite a long time ago. And he's also involved in project management for smart pre-project engineering in Saudi Arabia. And he manages standard design, change approval, advanced technology development, and global commercialization. I would like to invite Mr. Kang now. You have 15 minutes to deliver your presentation.
Thank you so much for your kind introduction. And good afternoon, ladies and gentlemen, and distinguished guests. I'm Han Ok Kang, and it's my honor to introduce Smart Project for Indonesia application at this SMR webinar organized by Batan. The title of my presentation is, as you can see, the Smart Development with Validated Technology. Next, please. Okay. Should I go to? Okay, good. Okay, thank you. Smart is an integral reactor. It electric power about 120 megawatt, which is about 1/10 of large nuclear power plant. Smart application is not only for electric generation. You can also use smart for the seawater desalination and district heating and process heat supply like hydrogen generation. Smart can supply in combined way 100 megawatt electric power and 40,000 tons of fresh water. We expect you can provide this electricity and fresh water to 100,000 population city concurrently. Next, please. This slide shows our smart development chronicle. Since 1997, our institute and Korean nuclear industry together have been developing small modular reactor smart technology together. In the early development stage, we focused on basic design, reactor design, and safety system development. At the later stage, whole plant design, including balance of plant, turbine, and auxiliary system, fully covered for standard design approval in 2012. In 2015, Korea and Saudi Arabia launched 3-year first-kind engineering design project for the construction of smart in Saudi Arabia. Next, please. In 2015, Korea and Saudi Arabia signed an MOU for the Smart Partnership Cooperation. To reach this agreement, two countries performed joint feasibility study for smart deployment and identified mutually beneficial cooperation. This form of cooperation is not typical between technology seller and buyer. Two countries become joint owners for smart commercialization. We jointly develop technology, shared the ownership of smart technology, and currently you are jointly promoting smart for global SMR market. Next, please. Now I'm talking about pre-project engineering. This project is the first phase for the smart partnership cooperation between Korea and Saudi Arabia. The project period is December 2015 to November 2018. The purpose of this project is to detail site-specific engineering work for the smart construction in Saudi Arabia. The work scope including reactor system, fuel design, and balance of power plant and main component design and validation. And based on this design work, we produced preliminary safety analysis report for the licensing. Major industry of Korea, including KECO ENC, KECO NF, also Doosan Heavy Industry participated in our project for their expertise. Kerry also operated the Human Capacity Builder program for knowledge transfer, which was consist of CRT Basic, CRT Technical, and OJT and OJP. Actually, 48 Kakia engineers are stayed in Kerry and participated in the detailed design work for the as independent author. Next, please. This figure shows our smart integral reactor. As you mentioned in integral concept, major components like core, steam generator, and pressurized located inside reactor vessel to remove large break local. There is no large penetration through reactor vessel. All these small penetrations are less than 2 inches and are located above the top of steam generator. This is very good feature in viewpoint of local scenario. The reactor coolant pumps are can motor pump and horizontally mounted above the steam generator. Helical steam generator are one-through type and produce superheated steam without moisture separator. We are using 57 conventional fuel assembly with used ceramic fuel. You can also consider accident tolerant fuel. So currently Kerry are developing ATF fuel, and as mentioned in Rosatom, the introduction of ATF can increase significantly the generation of hydrogen for the severe accident. The flow mixing header assembly located below the steam generator make core inlet temperature to be very uniform. The very good feature for the uniform of the whole temperature distribution. Next, please. Form of page. Okay, good. All the safety systems of smart operate in such a way the operator action or electric power not necessary for the safety function during design-based accident. The typical safety system of smart are including passive safety injection system and passive residual heat removal system and containment pressure and radioactivity suppression system. All these systems are operate based on natural force like gravity, pressure difference, and water-full radioactivity suppression. Therefore, safety system can operate not depending on electric power from emergency diesel generator. Safety-grade battery provides necessary DC power for valve initiation and post-accident monitoring. So basically, related to the Fukushima accident, the smart doesn't go to the, even without electricity or station blackout condition, smart reactor can make some safety condition without support of electricity. Next, please. Smart has been designed to locate the coastal area now currently. Of course, you can change the smart architecture engineer to build on inland, but current version of smart is based on coastal area. So in this figure, you can see seawater intake structure and other building like chlorination building in yard. Power accommodates reactor containment auxiliary building, turbine building, and one compound building in the between the two reactor building. One big characteristic of smart architecture is that reactor containment building and auxiliary building are integrated into one building. We call reactor containment and auxiliary building. This building is a seismic category 1 reinforced concrete structure. So this is basically for the small and modular plant concept, and we combine the two buildings into one building. Also, you can see the compound building between two buildings. The compound building for the access control area, radio waste treatment, and hot machine shop. Next, please. Throughout to the smart development, comprehensive design validation and verification programs are completed. Series of tests and experiments are carried out to examine physical phenomena related to the specific smart design concept. Two kinds of integral test loops are used to investigate thermohydraulic performance of smart and simulate various transient conditions. Small-scale facility, VISTA ITL, and large-scale facility, SMART ITL, is built inside the carry boundary. If you visit carry, you can see these two facilities. SMART ITL is the real height scale 1:1, and the volume scale is 1:49. It's a very big, huge facility to examine some hydraulic feature of smart. These facilities are used to understand the thermohydraulic behavior during operational tangent and design-based accident and simulate local scenario. Local tests are performed for verification of our safety analysis code. We call TAS. TAS is the specific in-house code for the accident analysis. In addition, natural circulation tests for the primary current system and passive residual heat removal system are also performed using this facility. Next, please. Technology validation is a very big, significant feature of smart design. Smart adopted conventional fuel, considering the different operational condition assembly height. Several tests are completed, including critical heat flux, hydraulic test, and mechanical integrity test. SMART ITL is the integrated thermohydraulic test for the SMART. These facilities can simulate reactor coolant system, passive safety system, and some simplified VOP part. Okay, thank you. I appreciate. Okay.
Okay.
Okay. Yeah, I go to this page. Yeah.
1-2 minutes more. Thank you.
Thank you. Thank you. Here, the next. Okay, you next please, and next please. During the smart pre-project engineering, there was a design change, including power omniating and fully passive safety system for better economics and safety. So, Kerry and Kakir and KHMP applied new standard design approval for our current design. So, this SDA project entered regular technical review phase after compliance review of docketing. So, we expect that final safety evaluation report will be issued end of next year. Next, please. Next, please. Okay, now I'm talking about some business model. Now, Kerry and Saudi Arabian side, Kakir are joint owner of smart technology. Recently, Korean KHMP began to play a role as EPC for global smart commercialization. So, smart team consists of Kerry, Kakir, and KHMP now. I think it is the best combination for the smart development, deployment, and global commercialization. So, below you can see the picture developed by IA milestone approach for the which is very holistic and consider 19 specific infrastructure issue. So I think that the smart team is ready to develop optimal business model in each country for better financing, project structure, and long-term operation. We applied this kind of approach for the some new country like some Jordan, Philippines, and some other countries. So we found that the smart can be very good optimum candidate for those countries. It is the very competitive construction cost and levelized electric cost. Next, please. So I like to summarize my presentation. SMART can be utilized for the multiple applications, including electric generation, theater, desalination, and process heat. SMART design is a mixture of innovative concept and proven technology. And new technology is proven through the comprehensive technology validation program using various experimental facilities. Now, Korea and Saudi Arabia jointly have ownership of SMART technology and cooperate for the global commercialization, and two countries are ready to cooperate with the newcomer country, including Indonesia, to deploy SMART technology. Next, please. Thank you so much. 감사합니다. Assalamualaikum.
Thank you so much. Thank you so much. So thank you for the presentations. It's an interesting cooperation between Korea and Saudi Arabia to have joint ownership of SMART and to cooperate and work with potential newcomer countries to deploy the technology. Thank you.
Thank you.
So our next speaker, thank you. Our next speaker is Mr. Benoit Lepouze. He's a senior advisor at EDF France. He's in charge of the relations with international organizations for the nuclear new build in EDF. He is also responsible for several development projects in Europe and in Asia. He has been working for more than 20 years with EDF and has an experience at the international working level for the IAEA as well. So you have 15 minutes to deliver your presentation. You can start.
Thank you. Thank you, everyone. Good afternoon, everyone, and good morning to some of you. Can you see me? Can you see my slides?
Yes, sir.
Okay, let's proceed. So we have an history of exchange with Indonesia, not only in nuclear, but also in generation, in renewables, in the grid, with smart meters. But of course, we also talked about the SMR lately. In 2018, there was a RFI launched by the Ministry of Research, Technology and Higher Education. So we replied to this RFI, and one chapter of our reply is specifically on SMR technology in development at the time of the consultation. So if you want more details, you can find a lot of them in this response, which is covered by an NDA. We also organized a Franco-Indonesian seminar in June 2019, last year. This seminar took place in West Kalimantan, near the site of a potential SMR. We exchanged on the technology, of course, but also on the development of the needed nuclear infrastructure, because SMR are quite similar to large reactors in this regard. You still need to have a nuclear infrastructure. And it was mentioned by your minister, you had an Indian mission, I think, in 2009. This is an important point to note. Luckily, Indonesia is knowledgeable about nuclear, but we are ready to provide our assistance, not only in technology, but also in the infrastructure development. Since then, our technology, French nuclear technology, is now branded a new word. I will come back to that in a few minutes. So what are we trying to achieve with this design? We are trying to replace a 300, 400 megawatt coal power plant with clean and competitive energy. We know that electricity is a key vector for limiting CO2 emissions, but the share of fossil fuels is quite large and still remain high. So there is definitely a need for small power outputs, a few hundred megawatts, which are dispatchable. The issue we have, if we want it to be competitive, is that we need to have not just modules, but a set of modules which are going to be competitive with coal power plants with a reasonable price of carbon. So that's the reason why we wanted to develop a design with 2 modules and not say that we need 4 or 6 or 10 or 12 modules to make it competitive. So that was really our goal. And to do this, we decided to develop a safe, because if it's not safe, it's not going to be marketable, simple and competitive reactor. High level of safety, with an architecture without primary loops, which means no loca, high resistant to hazards with large grace period. We wanted it to be simple and competitive with simplified and optimized architecture, passive systems, and very compact reactors. And we also wanted it to be flexible, not only in terms of electricity, but to also allow other applications such as combined heat and power, desalination, and maybe even hydrogen generation. So this is basically what you see on your screen right now is basically what I've just said, but in picture. We want to replace a coal power plant, 300 megawatt, 400 megawatt, with a clean energy unit. New World is a semi-buried design, which has two advantages. One is for acceptability, and it needs to be also noted that the EPZ is limited to site boundary, which is also a strong point in public acceptance, but also it makes the design quite resistant to external hazards. So if we want to dig a little deeper in how the design is how the reactor is designed, we have, don't know if you can see my cursor. We have the pressure vessel, which is integrated with hydraulics and upper internals. And this pressure vessel is then inside a steel containment, which is on the right, where we produce the electricity from the steam, which comes out the pressure vessel. And we are now in the process of optimizing the nuclear island layout for a 2-reactor configuration. We are optimizing this layout in order to make it, once again, competitive against traditional power plants. So if we want to talk about the progress in this summer, we have a set of mock-up to the manufacturing process of our compact steam generator. We have also experimentally validated the temperature and pressure of our compact steam generator in steam generator function. We have hermetic technologies for the control rod drive mechanism, which is also integrated as was shown before. And we have also tested the in-vessel wiring under high temperature and high pressure. This is where we stand right now. So we started in 2012 with a study of feasibility. We then had a pre-conceptual design until last year. We are right now in the conceptual design with the aim to enter basic design in 2022 and having a detailed design and licensing from 2025. The aim is to have New World available as a commercial solution by 2030, which means that we'll probably have to have a fork constructed either in Europe or North America. New World is open to international cooperation. It was announced that it was branded as New World during the General Conference of the IAEA in September 2019. It is, in fact, the collaboration of several companies, EDF leading the development with the help from CEA, from Naval Group, and from Technical Atom, who have a long experience regarding marine reactors. But on the same day, we also signed a framework agreement with Westinghouse, quite well known in PWR technologies, in order to explore potential cooperation on SMR developments, which means joining New World. So we are definitely open to international cooperation. Regarding local industry involvement, I've mentioned that we want to make it competitive, and competitiveness of SMRs means that you need to have parts built in factory, and you need to gain on series effect what cannot be achieved by size. That means that we cannot promise that every part will be localized to every country where we're going to construct it. But some portion definitely need to be manufactured locally. And the French nuclear industry has a long experience of managing supply chain for large reactors. The same methods are going to be used to qualify local suppliers. It is too early to quantify exactly the level of localization which can be attained. But if a country would consider a fork project in the country, such as Indonesia, more localization could obviously be considered because companies would be joining the new world core suppliers. Indonesia could then become the regional hub for the technology. To sum everything up, we are trying to really design a reactor which are going to be around 300, between 300 and 400 megawatt. Right now it's 340 megawatt net power, because we want to have a solution to replace coal power, fossil fuel. We want it to be safe as the latest generation 3+ reactors. So that means taking lessons from Fukushima event. And we are open to international collaboration with the aim to have a commercial product ready by 2030. Thank you.
Mr. Lepose. Thank you. So we have heard about the technology of readiness of your reactor technology. And so by 2030, yeah, it could be ready for deployment.
Correct.
And also thank you for pointing out the localization, the local content that can be, that can be, given to embarking countries like Indonesia. Thank you. So our next speaker is Mr. Bin Chen from China National Nuclear Corporation. He is a senior project manager of China National Nuclear Corporation for International Marketing and Project Management. Previously, he was working in Nuclear Power Institute of China as a senior engineer. He has international experience and has been participating in the design of most Gen 3 as well as advanced reactors. I would like to invite Mr. Bin Chen. You have 15 minutes to deliver your presentation. This is the last presentation of the speaker, and after this we go to discussion. Thank you.
Thank you, Chairperson. I'm going to give my presentation. Is that clear?
Yes, sir.
Perfect. Thank you. Thank you, sir. So, good evening, good afternoon for some of our attendees. Good morning. I'm Dr. Bin Chen from China National Nuclear Corporation. And in the next 15 minutes, I'm going to give you an outlook of small modular reactors, as well as the latest updates of demonstration projects in China. And first, well, sehingga, I hope my pronunciation is good. And at the very beginning, I would like to say congratulations on your National Science Day of Indonesia, as well as the facilitation of IAEA on this activity. By the opening, I would like to give you a brief introduction of our corporation. It is called the China National Nuclear Corporation, founded in 1955 as the former Ministry of Nuclear Industry of China. And so far, we have more than 700 subsidiaries. And just very beginning of this year, our company become one of the members of the Global Fortune 500. We have more than 153,000 employees, and nearly half of them are professionals or senior engineers. We are the leading corporation who owns the most nuclear power plants in China, as well as the only few supplier with the most comprehensive nuclear industry supply chain. And why we have devoted so much? Because there are only 2 demonstration SMR projects under construction in the world, and we are the only company implementing them. So today I'm going to give you one introduction for small modular reactors called ACP100 and another one for high temperature gas-cooled reactor. Here is a list for the design features of this ACP100. It is what commonly known as the integrated pressurized auto-reactor. You have already seen some similar ones like the loose scale and other operations. The main feature for the electrical capacity is 125 megawatts. The most benefit is that it's as the integrated design, we can eliminate large loss of coolant accidents and greatly enhance the nuclear safety. The construction of this demonstration project is already started this year in Highland. Another one is what we called, normally known as the high temperature gas-cooled reactor. And the electrical capacity is 105 megawatts. The efficiency of the turbine is much higher compared to the PWR because of the cold exit temperature is much higher. It reaches as high as 750 degrees centigrade. So there is a great practical feasibility for the hydrogen production for the future. And this demonstration project is already under commissioning and expected to be operated next year. And as the topic of our webinar today, I'm going to give you the detailed introduction. First, the safety of SMR by its design, and later then the progress of our demonstration projects, and jump to the summary as the last part. The safety, what we call as the safety by design. Taking airplane as one example, that the gravity would always draw the airplane to the ground. So the design should follow the natural law. For example, as the passive safety by design, we have all these water tanks on the top of the nuclear power station, and gravity-driven water injection will keep the core flooded. And by the design of these passive systems, the residue heat will be removed and the core will stay safe as cooled. But as for the high temperature gas-cooled reactors, the safety is guaranteed not by the system, but by the characteristics of the fuel. And this is what we call the trickle fuel. It is a ball which the outer part is made from the nuclear class carbon. But the most important part and the part which guarantee the safety is what we call the silicon carbon. Yeah, we call the silicon carbon layer is so strong that the radioactives are unable to penetrate. And this is the unique material characteristics for it. I can see some of the participants today are asking the questions about accident tolerance fuels. And I would like to emphasize here that one of the material as the candidate for this ATF fuel is also silicon carbide. And this material is now already used for the high temperature gas-cooled reactor. And because of this fuel is so small, and that makes it so strong. Another part I would like to emphasize here is that for the silicon carbide, with all these operating experiences, that the radioactives which is contained within these very tiny balls only starts to diffuse, which means start to have this tiny leakage beyond, which is above 1,620 degrees centigrade. And by comparing with that, the normal fuel cladding material, what we call the Z-alloy, which is used within the PWR, they are failed beyond 1,204 degrees centigrade. So there is a gap for almost 400 degrees centigrade. And this is where the safety margin relies. And by this inherent safety characteristic of the material, of the fuel, so that the reactor is so safe, it could keep its safety without any safety systems. And this is what a severe accident experiment performed on a real reactor. And I'd like to emphasize here again, it's not performed on a facility, not on an experimental facility, but on a real reactor that witnessed by IAEA, the very first experiment of loss of cooling combined with station blackouts and combined with the failure of reactor tree. And still, you can see, despite all these accidents happened, triggered, nothing happens here. Everybody is witnessing and laughing. So totally safe, totally safe. Another part I'd like to emphasize is the progress of the demonstration projects. China has already achieved remarkable progress for 2 advanced SMRs. One is the ACP100, started this year, and another one is this HDRPM in Shandong, Xidabei, with inherent safety features under commission and expected to be operated next year. And this is the on-site picture for this ACP100, and this site within the red matrix is the whole site for the SMR, which compared to a large PWR, and you can see how less land it could take by an SMR, which is much more economic, feasible, and more flexible for your site selection. Another part is the HDRPM demonstration project. You can see all the buildings are already there, almost finished. And we have also successfully manufactured the first main blower, which is the main pump for the gas speller, and as well as the first steam generator for high temperature gas reactors. And we are quite proud of that. And why this is so important, why China has devoted so much resources into the development of SMR, because it plays a significant role in not only energy conservation, but also the reduction of carbon dioxide emission, which is a promise of our government to the world, as well as the environmental protection. And the promote of these advanced nuclear technologies is not only supported by the industry, but also promoted by our regulators. And one of the most important aspects are the, also mentioned above, is that the preparedness of the emergency evacuation. So there is also an alternative regulation for SMRs, and we have our National Security Authority have issued the guidance on emergency preparation for advanced SMRs to further not only enhance the safety of the SMRs while providing a more flexible way for the utilization of this technology. And China will continue to promote the comprehensive utilization of nuclear energy for greater contribution to the global development, because nuclear power is the most mighty power source we have mastered so far for all human beings. And also mentioned by other presenters before, we do believe that the milestones from the IAEA recommendation is vital for development, especially for embarking countries. And China, as well as our company, we are more than happy to share our experience on the transfer of technology, the localization of manufacture, sharing of experts, investment, and etc. By the summary part, I would like to again emphasize the SMR, which is integrated design as a PWR, the HDR with its unique inherent safety feature, and also potential for multi-purpose industrial application, that we are always open to international cooperations and sharing of our experience. And also, we do believe that even for demonstration projects as a research reactor, that the high temperature gas-cooled reactor is quite fitting the unique role of the multi-purpose application. And also one more thing I would like to mention today is that for ITER, the artificial sun for all mankind, this is an international project which has been under construction and under commission for several decades. And for the, especially for the forecast of the future, that as the grandpa of my grandpa has mentioned, that we are only 50 years away. But as the era of my grandpa, it is still 50 years away. But however, last year, there's an aggressive announcement that now we are only 40 years away from our own sun. Why? Because I do believe that for nuclear industry, after Fukushima and after COVID-19, we are facing a kind of hard situation. But despite of how hard a nuclear is, our mission is to break it and to absorb the energy for a better tomorrow. And thank you for all your participants. And that's the sharing of my presentation today.
Okay, thank you so much. Thank you so much, Mr. Chen, for the presentation. And now it's 1800 hours local time. We would like to move to the discussion. We are 15 minutes behind. I would like now to start with the questions from the panels. We have a panel of experts here, and I would like to ask Professor Zaki Suud from Bandung Institute of Technology to ask the first question.
Can
unmute the speaker.
Oh, yeah. Thank you. Okay. Can we hear? Okay.
Ask the question. Yeah.
Okay. Nuclear power plant expansion have lost its momentum due to some severe accident. SMR can be game-changing to regain and accelerate nuclear energy market expansion. But this need two factors: factory production, excellent NPP production at factory, and also it needs excellent business development. My question is, first, when will the effective and efficient factory production can be realized according for your NPP? The second question, how far overall NPP construction can be reduced by effective factory production? The third question, Indonesia is area with very severe earthquake. Some even consider the earthquake even bigger than Fukushima case. My question, to anticipate such extreme earthquake condition, what type of enhancement need to be conducted for your NPP design? Thank you very much.
Professor Saki, do you have any specific vendor, or we can just ask
For all.
Any vendors to ask?
For all vendors.
Okay, so be quick to all vendors for the 3 questions. I think, okay, we can start with NewScale because NewScale was the first presenter. NewScale, please, Ms. Collins.
I think if I understand the questions correctly, he asked about factory fabrication and when we will be ready. The NewScale design, as you know, as I mentioned in my presentation, we are starting the manufacturing trials, and we will start the first forging release in 2022. So we are essentially going to be ready to deploy per our commitments with the U.S. Department of Energy. We will be ready with our first module operational by 2027. Now, the customer UAM's schedule is 2029, and that's specific to the customer and their requirements with respect to the coal plant retiring and how they are managing getting the new NewScale power plants online. So it goes with their schedule. The second question he had, I believe, was the construction time. The construction time for us from the time of the first safety concrete pour to the first module COD is going to be 3 years. And I don't recall the last question. Catch that one.
The condition of Indonesia, what type of safety enhancement that can be provided by your design?
Right. So as you know, the NewScale power plant is below grade and essentially is in a seismic category 1 building. As I mentioned, that it is resilient to natural disasters such as earthquakes, hurricanes, floods, and also resilient to aircraft impacts. And from a seismic perspective, we have up to 5 Gs is what we have analyzed. 5 Gs is what we have analyzed, and compared to what the standard is for the industry.
Ms. Collins. Next, the Rosatom Overseas, Mr. Mosfin, if you want to comment.
Yes, let me comment shortly. So first of all, we have the ideology of maximum fabrication of all the major equipment at the fabrication facility. The largest part of the equipment is the RPV. It is fully produced at the fabrication site. The weight of it is 146 tons, as I showed in my presentation. That modular construction and high prefabrication allows us to minimize the construction period by up to 3 years, Yeah, the full construction of the next of a kind nuclear power plant will be 3 years. The first one would be 4 years. And the third question was about the regulation, and the local enhancements. We presume that, of course, we take into account the potential high seismic in Indonesia. And as I said, our reactors were evolutionary developed from those placed on our icebreakers. And there you may understand the vertical and horizontal accelerations are very severe. And that is why the RPV withstands the maximum acceleration of up to 3G. The nuclear power plant itself, of course, slower, but that depends on what how you want to calculate the potential accident, you want to assess the potential accident. And of course, the nuclear power plant is resilient to all possible external events like tornadoes, the fall of the aircraft, and all the rest. This is actually discussed with every customer on a separate, within the separate discussions. And some customers want to provide for the tolerance of the nuclear power plant to the fall of the nuclear power plant. Some manage these situations in a different way. We are ready and open, and we have this kind of experience based on the construction projects of the large nuclear power plants. Thank you.
Must be next, Mr. Kang from Kerry.
Okay. First question is about looks like modularity. So basically, SMART is integrated reactor. All the main components of reactor system located inside the reactor vessel, and so I think that the most of component of reactor system can be manufactured in factory and can be transported to site, and the necessary work for the site is very minimum. So the concept of modularity can be very easily implemented in SMART project. The second question is about construction period. So basically, I think that the value is very same. We expected from first concrete to COD is about 3 years. So that's just our target value for the first SMART project. And third, the local condition related to safety and some safety related to Indonesia. I want to talk about our experience with some. Basically, we estimated this kind of issue in Saudi Arabia, Philippines, and Jordan. For the Jordan and South Jordan, we consider some inland condition, and for the Saudi Arabia, we consider onshore condition. I think that in the case of Indonesia, the onshore site is some more expected. So for this condition, we examined some flood and seismic condition, and some several some aspects can be crucial for the safety. So our estimation is that SMART can be there's no issue related that applying the SMART in the Philippines and Saudi Arabia. So I'm not sure the exact condition of Indonesia, but based on our some visual study for two countries, SMART can be easily deployed in Indonesia. But yeah, that's just my answer for the question. Thank you.
Mr. Kang. Next, Mr. Lepouze.
Thank you. Well, regarding the first question, which is, I believe, the readiness of the factories, basically the factories are here because we are relying on existing technology. So I don't believe that factories are on the critical path, and I believe it is the case for any design we've talked about today. Regarding the construction time, our design is supposed to be constructed. I mean, we design it so that it is to be constructed between 3 and 4 years, probably closer to 3 years. But the first, the fork, of course, will be more like 4 years, we believe. The last question, I believe, was about the resistance to earthquake and external hazards. Or semi-buried design makes our design extremely safe. And as was mentioned before, since it comes from marine technologies, the reactor pressure itself is also very resistant to high acceleration. But
next, Mr. Chen,
to be confirmed in the safety case of a particular plant.
Thank you, Mr. Lepouze. Next is Mr. Chen. Can you comment on ACP 100?
Yes, also. As for ACP 100, actually, it took a longer way as the other products, 3 to 4 years, and which is depending on the local site situations. For the factory production, actually, it has already being practiced in China, and we are quite happy with the readouts. And we do believe it could significantly accelerate for the nth kind, and especially for the large-scale deployment. And as for the enhancement of the reactor safety, depending on the very specific situation in Indonesia, as well as the sesame part I do believe the volcano situation is one way we need to take into consideration for the external hazards. We do have some experience for the local parts, some of the sites in China, and we hope that this experience could also be useful for the site selection in Indonesia. Thank you.
Chen. Next, our second panel is Mr. Sugeng Triwono from Indonesia Power. Please, you can ask your question now.
Thank you for this opportunity. My name is Sugeng Triwono from PT Indonesia Power, the power generation company. With Batan, we actively support and contribute to implement the first NPP in Indonesia, and hopefully will be operated by our company. And then my question is addressed to Mr. Stefano Monti from IAEA. The question is, expert always says that nuclear power plant is completely safe, with accident risk considered to be very, very low. Therefore, one nuclear power plant is on accident, say because of, say, technical accident or natural disaster or terror attacks that lead to radioactive emission becoming uncontrollable. So do you think from the IAEA perspective or experiences that government of Indonesia shall cover all damages caused by the accident, or the insurance company that's liable to cover damages that happen? Thank you, sir.
Mr. Monti, can you respond to the question? Short, please, in 2 minutes. Thank you.
Yeah, I'm not sure that I got the last part of the question regarding what is the assurance the one can.
Yeah. Do you think? Yes. Do you think that the government should cover the damages if there's radioactive emission, or is the insurance company? What do you think?
Oh, this is the
IAEA experience.
That of course the national government has an important role to play in the country. First of all, because of course it has to guarantee all the safety related issue. Regarding the insurance, well, we know that there are a problem with liability. However, the country remain responsible in front of the population and the international community regarding what can happen in any possible nuclear scenario at a nuclear installation.
Mr. Monti. Next, we will read the question from the chats first. The question for NuScale. Could you please comment on the shift of your FOAC dates to 2029 to 2030?
I think.
Are you still there? Yes.
It was from 2027 to 2029.
Yes. Yes, correct. Thank you.
Okay. So the first, as I mentioned, the first customer is UAMS, and UAMS essentially is a project-based action agency headquartered in Salt Lake City and has 47 utilities in the 7 states. And they revised their schedule to align with the timing for the UAMS member needs. So this schedule is also aligned with its retiring its coal generation, which is around 2030. And there are some decisions. They've taken a very controlled approach towards the power output, They're also looking, instead of wet cooling, they're looking at dry cooling technology. And so, and also considering their regulatory, the time that they need to get their site licensing done, they have extended, they basically have now mentioned that the COLA submission is around April of 2023. They anticipate approval of their COLA by, this is the site combined operating and license application. They anticipate the approval by November of 2025. It's expecting that the start of the construction would be by the December of 2025, and then the first module would be operating, the COD for the first module would be at mid-2029. So it has to do with them taking a relook at their member needs and with aligning their needs with respect to when they need the capacity with their coal power plant retiring.
Next, we have a question from the panel. We have Mr. Alexander Agung from the University of Gajah Mada.
Okay, thank you, Bu Johanna, for giving me the opportunity. I would like also to thank all the presenters for the interesting presentation. My name is Alexander Agung from the Department of Nuclear Engineering and Engineering Physics, University Gajah Mada. Here I have two questions. The first one is addressed to all presenters from the vendors. Human resources is one of important aspects of nuclear power plants, and involvement of local people, I believe, is very crucial during the whole phase of deployment. So my question is, how many workforce is required during construction, commission, and operation of SMRs, and roughly how many percentage of those workforces can be provided by local people? My second question is addressed to Mr. Mosquin, Rosatom. In your presentation, you mentioned that the refueling cycle of RITM FNPP is up to 10 years. What happened with the plant during refueling? Is the ship transported back to Russia for refueling, and how long is the downtime? If this is the case, then no power would be generated in the site. Then it implies that you need at least 2 ships inside which operate alternately. So could you please comment about this? Thank you.
Alexander Agung, for the first question, we can start with NuScale. Short answer, how many workforce and what is the percentage of local human resources?
So the NuScale power plant, during normal operations, we have 300 highly qualified employees that will operate the plant. For localization, the balance of plant, I explained that the power conversion systems, the skid-mounted, turbine-generated condenser, etc. So most of the balance of plant, especially with the EPC scope, 80% of that can be localized. There's certain materials like alloy piping or safety-related valves that essentially would be imported. Now, the NuScale portion of the scope, which has to do with the NuScale power module itself, we believe about 20% of the NuScale scope could be localized. And that would include like printed circuit boards for INC, mechanical handling systems can be localized. For sure, a large portion of the labor force, which is a significant portion for construction, that can be localized. And I think during the peak hours of the construction, it's around 3,000 people that will be participating in the actual construction of the power plant.
Mr. Mosquin, you can also, okay, Mr. Mosquin.
Yes, thank you. Let me start with the amount of personnel which is needed to construct the nuclear power plant. Currently, we are at the stage of the conceptual design development, and we think that we will have the exact figure on the technical design development phase. So currently, I cannot give you the exact figure for the amount of personnel which we need to construct the nuclear power plant. When it comes to the operational personnel, we need about 100 people to work at the nuclear power plant during the daily operation of it. Around 50% of that is operational personnel, and the rest is administrative staff and some reserve personnel. All those specialists might be local, so we don't presume that Russian personnel shall operate a nuclear power plant in case of the EPC model of its construction. When it comes to BOO, we may decide it jointly. Some amount of personnel might be brought from Russia to support the operation of the nuclear power plant or to manage the company, but of course a large amount would be local. And when it comes to the refueling of the floating nuclear power plant, we take the nuclear power plant for refueling and for all fuel-related operations to Russia. It takes around 1 year to go through all of those operations, and you are absolutely right that we shall provide a substitution for that floating power plant during this period. And we presume that our business model provides that at least 7 or 8 floating nuclear power plants will be simultaneously constructed and almost simultaneously constructed. And while one goes to refueling to Russia, the other one substitutes that immediately. Thank you.
Mr. Moskin. Mr. Kang, please.
Okay, so about first I have to divide into the construction phase and operating phase. For the construction phase, the estimated the maximum, of course the necessary manpower is changing depending on the construction phase. Initial stage very small, and in the middle of construction stage very the big number. The maximum number, the estimate is about 8,000 some people necessary for the two smart unit construction. Among that, the 1/3 is related to some nuclear island, and 2/3 is for the conventional island. So I think that the possible localization is mainly possible for the initially some commercial island. So based on this, I think that about some 5,000 some manpower can be taken by Indonesian some company. So that's my expectation. And about the operating phase, I think I can give you this response based on our Baraka APR 1400 project. In the case, all the operate is trained by KHMP, and basically all the plant is operated by local people, some UA engineer. So I think that that kind of scheme can be applied to Indonesia. So basically all the operator can be taken by Indonesian engineering part, and for the maintenance and some repairing work, that initially you need maybe some support from KHMP, some Korean company, but basically some first year, second, and some 10 years, after 10 years, the whole scheme can be done by Indonesia operating company. Some can be smoothly, you can increase the localization portion to that operation part. I think that's just the effective scheme for the smart application in Indonesia. Yeah, that's my case answer. Thank you.
Okay, thank you, Mr. Kang. Next, Mr. Lepuse.
Sorry, thank you. We are also in conceptual design, so it's hard for us to give any figures regarding construction. If you want to take an analogy, you have several thousand people working on site for large power plants, but it's not the same kind of construction. So I don't expect that you would have the same number for an SMR. And you need to have also keep in mind the fact that SMRs will be constructed mainly in factories. So it largely depends on the level of localization that you want to achieve and whether you want to participate in a fork and be a regional hub or not. Regarding operation, of course, these people are going to be local, 100%. I mean, you may decide to hire external advisors, but the operator will be fully Indonesian. And for an SMR, you should count between 100 and 200 people, depending on the outsourcing policy you want to have.
Jose. Next, Mr. Chen. Mr. Chen, are you there?
Yes, I'm here. I was mute, and yeah. Okay, thank you, Chairperson. And first, I would like to answer the question about the how many people will be there during the construction, commissioning, and operation. For the construction, it is normally less than 2,000 people, and since this is the first project, and we are expecting to have less people for the following projects. For commissioning during the peaking time, it will be slightly more because of these tests on-site personnel. And for operation, it will be less than 200 people. Though there's one tricky problem for the multi-purpose application, which means if you do have the heating or other application like sea-water desalination, you do need more staff on the other plants and with other expertise and to be well trained, of course. Another thing is for the localization, and we totally believe with the technology transfer as well as the cooperation, the construction personnel as well as the operation staffs could totally be depending on the on your task force and the people from Indonesia. Of course, with well certification and training.
Thank you so much. We have our last panel. We will extend for about 10 minutes max. Mr. Azizul Kakim from our regulatory body.
Thank you, Bu Joanna. Everybody hear my voice? Well, first of all, I would like to appreciate all of the presenters for excellent presentations. And I have to raise one question for all presenters. The first one is that due to the first of a kind technology, SMR technology deals with a regulatory issue because there is no reference technology before the first one. So how do you deal with that issue with your national regulatory body? That's my first question to all presenters. And my next question is to Mr. Moscovin from Rosatom. How do you define emergency planning zone for moving nuclear power plants such as ice breaking, floating power plant? And how do you conduct emergency drill for that type of reactor technology? Thank you.
Okay, thank you, Mr. Kakim. So we have the first question for all the vendors on the reference technology. We can start with NuScale.
I believe the question had to do with regulatory challenges. As you know, the design was just approved by the U.S. Nuclear Regulatory Commission for the NuScale SMR. So the question would be, for me, can the in-country regulator, in this case, the Indonesian regulator, accept the US NRC design approvals? If there are bilateral agreements in place, then you can envision where the country, Indonesia in this case, would work with the US NRC in collaboration to license the technology in country. We can also envision what we're doing in Canada, for example. We're doing a pre-licensing vendor design review and essentially looking at a gap assessment. So we can also envision, if a country is following the IAEA framework, envision going down the path of doing a gap assessment between that and the US regulations to see how the regulatory license could be moving forward in Indonesia.
Next is Russia. If you want to answer the next question, there's also this issue about the transportable nuclear power plant and how your neighboring country, they're concerned about it.
Yes, thank you. So with regards to the first question, we plan to implement the same approach to licensing as for the large-scale nuclear power plants. We have quite a different licensing system in Russia. We don't need any standard design approval, and we just go into the site license. With this in mind, we are working with our regulator right now based on the standards related to the large nuclear power, the same as for the large nuclear power plants, but at the same time discuss that maybe some codes and standards shall be amended. Say at least we have carried out some necessary research, and Rosatom estimation is that the SMR NPP emergency planning zone should not exceed the NPP site, which is unlike the large nuclear power plants, where the EPZ may reach several kilometers. And as to the floating nuclear power plant, the conceptual design, the sanitary protection zone, the buffer area, is within the vessel itself. And when it comes to the emergency planning zone, it is 1 kilometer. And if we talk about the agreement of the neighboring countries, this is just the same as with the large nuclear power plants. We need to go through this talks with the neighboring countries to get their support for the project. And I need to say that when we transport the nuclear power plant, the floating nuclear power plant, there is no need to go through the territorial waters of the neighboring countries. We are planning to use the dock-wise vessel and transport the floating nuclear power plant through the international waters, which excludes any talks to the countries on the route of the floating nuclear power plant. And it is carried out just like a nuclear material. We license it in Russia as the normal civil vessel, and then just transport it on the dock-wise as the nuclear material. And that's all I think.
Yes, thank you very much. Mr. Kang, please.
Okay, so I think basically some nuclear plant license is based on the policy decision by own country. So basically we'll follow the Indonesian regulatory bodies some decision. Basically there can be some kind of regulation approach, some European or Russian or United States. So anyway, we will try to satisfy the Indonesian regulatory bodies approach for the SMR licensing. But for the SMART, you already got a standard design approval for the SMART in 2012, and currently we are doing some additional standard design approval for some power alternating and passive safety system. We think we can get the license on next year. So for the Indonesian application, I can say about some Baraka UAE project. UAE project, the FANA, the regulatory body of UAE, some uses some the reference of the domestic APR 1400 license. So they used that domestic license for their application. So I think that's a very good reference for the Indonesian application. Basically, Indonesian regulatory bodies decide what do their licensing work for the safety of their own people. But domestic and the smart licensing standard design in Korea can be good reference for the licensing. That's for the some technical part. I think that's just my response for the question.
Mr. Lepose.
Yes. First, let me remind you that our government has just included nuclear technology and SMR technology in the revitalization plan after the COVID crisis. So we have support from our government. We have some governmental funds, and those will be directed at refining the design and licensing it. So licensing it should not be an issue because we are using proven technologies. But at the same time, the real issue with licensing regarding SMRs is not the licensability. We are convinced it's licensable, but the fact that we can keep a unified design to have this, to gain from the series effect. And that is the issue, because we are not going to build the reactor just for France. And we don't believe that a country will build the reactors just for its country. For example, in France, we want to keep large reactors. But there are some places where large reactors are not suitable, islands, for example, and that's the reason why we develop this technology. So the real issue we have with licensability is to unify license. And that is exactly the idea we had when talking with our partner to be Westinghouse, which is a discussion on harmonization of regulation. And this is exactly what we are pursuing. And we are trying to find people interested in our design and to construct clubs for which we would have regional hubs in order to enlarge the number of reactors which are going to be built, and then we can reach competitiveness. That is the issue with the licensing.
Mr. Lepose. Mr. Chen, please.
Thank you, Mr. Chairperson. My answer to these questions, first, I would like to emphasize with our design, we do have implemented a lot of innovative technologies, but that is exactly why we start our demonstration project so early. And we would like to provide for our partners for a proven technology and be practical and be with engineering experiences. And this is why it's so important for demonstration project. Another thing for the standards for the licensing, I would like to emphasize here that despite we do have our own standards, we do have quite transparency comparison for all different standards. Because you know, China, we have all the nuclear power plants from all design. We do have the design from US, from Russia, as well as from France. So we do have knowledge with engineering practice of all the different standards there. And that's one kind of knowledge we can provide. Thank you.
We have a remark from one more. Actually, we are running out of time, but we have Mr. Arya Rahmadi from our technology agency.
Yes, hello, Ibu. My name is Arya Rahmadi. Can you hear me? Hello.
Yes, we can hear you.
Because,
yes.
Yeah.
Because, well, yeah, thank you very much for having me. My name is Arya Rahmadi. I'm working for the Agency for the Assessment and Application of Technology. Actually, my question has been covered by some of the presenters, but I'd like to ask more about the level of commitment on the local contents, particularly from the NuScale and the Rosatom, The reason why this is very important because SMR, it could be less than 300 megawatt or could be 100 megawatt. It's suitable for Indonesia, particularly that we have a lot of islands. We are island nations. And secondly, we have also strong manufacturing capabilities, particularly for the steam coal-fired power plant. So I guess, would it be possible if we can be the hub for the manufacturing, particularly in this region, for the non-nuclear island, for instance? Thank you very much. That's my question to Cheryl as well as to Rosatom.
We are running out of time, actually. Is it okay if we answer your question later on? We still have many questions from the chats. Yes.
All right.
And we will post the question. Yes, thank you.
No problem.
The questions and the answers in YouTube. I think for the commitment of local content and the hub, I think some speakers mentioned there will be like negotiation. It can be negotiated as well. So, ladies and gentlemen, we have reached the end of the webinar. Thank you so much for staying with us 12 minutes longer. And we would like to thank again all the speakers, Mr. Monty from the IAEA, Ms. Collins, Mr. Mosfin, Mr. Lepouze, Mr. Chen. We wish you all the success in your work and your technology. We would like to extend appreciation for the support from the Ministry of Research and Technology, to all the panels, the team, and those who have contributed to the conduct of the webinar. Please contact us if there's a problem with your questions or the registration for attendance and the certificates. Stay healthy and have a great weekend. Thank you.
Thank you. Thank you so much.
Thank you.
Thank you.
Thank you. Thank you so much.
Thank you, Mr. Johan.
Thank you so much. Thank you.
Thank you, all
Yes,
of you.
Mr. Chairman wants to say something. Yes, Chairman of
okay.
Batam, Professor Anhar. Yes, please.
Okay.
Sorry. Yes.
Please, Pak Anhar.
Closing
Okay,
remarks.
okay. I just take this opportunity again to thank you, all of you, all of the speakers, Mr. Monty, Mr. Collins, Mr. Chen, Mr. Carl, and also Monsieur Lepouze, and everybody who are attending this webinar. This is very great. So I hope that we can meet each other one day. So keep healthy. Again, thank you very much.
Thank you. Thank you.
Thank you.